Do you hear me? Is the microphone okay? Here? Yeah? No. Where is the, oh, here. Okay, yeah, well, so I'll talk a little bit about this, well, gas dynamics, I guess we heard a lot already before from Colby and Monica Colby, and I'm going to talk about some quasars in general and a particular model involving stellar captures, and then I'll mention something about something for implying LISA candidate events also. Colby already mentioned the Zoltan argument, so I'll go quickly through this. Basically, we observe some radiation and we measure the density of black holes, so we can compare the two of them to check that they're consistent with certain epsilon, which is an efficiency of radiation. And of course, that tells us, as Cole said, that the process of quasars must be substantial importance for building up the population of black holes, but at the same time the mergers of stellar objects could account for some part of that. There is, if we want to understand basically the way in which black holes have grown and the way that this relates to galaxies, there is two important things to know. So first of all, there is something must involve this quasar activity, because we see that quasars have contributed a very substantial part of the average density we see in nuclear black holes today in the universe. And at the same time, we see that nuclear black hole masses relate to the spheroidal part of the galaxy, the spheroidal stellar system. It's interesting that nuclear black holes don't seem to hold much of any relationship to the disks around them, the galactic disks, but it's to the spheroidal stellar system that they relate. So that tells us something important about how they were built up. And there is this well-known relationship that has already been shown between black hole mass and velocity dispersion of the stellar system around it. And the black hole mass goes as sigma to the 4 or maybe sigma to the 4.5. So, a lot of the models that you hear about to explain these relationships basically involve feedback, as Cole mentioned, but there is an alternative to that, and this alternative is what I'm going to talk about. The alternative is that it is not the activity of the AGN that basically shuts down star formation or determines somehow how many stars are going to be formed around the black hole, but rather it is the number of stars that are forming very close to the black hole. It is the star formation itself that determines how much fuel becomes available to the black hole, and therefore how much the black hole grows. And that's the alternative explanation, and so that's what I'm going to discuss. Now, the standard quasar model essentially says that the way that quasars are understood and they are explained is that you have an extended disk of gas around the black hole, and the gas, it just flows in gradually. There is some viscosity process, something that causes the gas to lose angular momentum, and it will gradually move to the center of the galaxy until it reaches the zone of influence, and then continue to accrete further to the center, and finally go into the luminous region of the accretion disk that we see as a quasar, and then go into the black hole. But one has to realize that this standard idea is not really supported by a lot of evidence, and it's actually hard to understand how that could happen. And to see this, just consider a typical galaxy, a large elliptical galaxy, which could have a total stellar mass 10 to the 11 solar masses. Then, according to the relationship between bulges and black holes, the black hole in the center would have about 10 to the 8 solar masses. This would be a galaxy with a velocity dispersion around 200 kilometers per second, and the half-light radius might be about 5 kiloparsecs. So half of the stars are within 5 kiloparsecs of the nucleus. Now, so how far in would you have to go to have something like 10 to the 8 solar masses of material in this galaxy, similar amount of material as what was required in order to grow this black hole to 10 to the 8 solar masses. Well, even if you had something as steep as a singular isothermal profile with density going as r to the minus 2, then you would have 10 to the 8 solar masses in stars within 5 parsecs. And normally, elliptical galaxies would have a profile that's flatter than this, then you'd have to go further away to find that much material. But the luminous parts of the accretion disk that would produce the light of a quasar around such a black hole would only be about 100 astronomical units across. And so then you have to explain how you go from 5 parsecs to 100 AU, how you carry 10 to the 8 solar masses all the way across these 4 orders of magnitude in radius. So, there is no way to account for this. Some people say that, well, maybe there is a lot of bars inside other bars which somehow can account for the transfer of angular momentum that you require to carry out all this gas. But actually, when you go to large radius, essentially in this disk out to 5 parsecs or so, or even further, and you compute what the structure of the disk should be there around a quasar, it should be quite cold and essentially gravitationally unstable. So the Tumor skew parameter of the disk is less than 1. So it should form stars. Why not? I mean, anywhere else in the universe where one sees cold gas in a disk, the Jeans mass is low, we see star formation happening. So why not in this disk around the quasar? Why do we think that instead of forming stars, the gas will just undergo some viscous process and smoothly flow to the center through these 4 orders of magnitude? So that's basically a problem, and I think that if we didn't have any observations about either quasars or nuclear black holes in galactic nuclei and their masses, and we just had to start from theoretical principles trying to predict what kind of black holes are we going to see in the center of a galaxy, maybe we would predict, well, there will be a stellar black hole, maybe it has grown to 1,000 solar masses, but we'd have no idea that the masses would have grown to 10 to the 8 or 10 to the 9 solar masses the way we observe. So the new quasar model that we have proposed in work with Juna Kohlmeier is maybe we can feed the accretion disk with stars. So black holes grow by accreting gas from a thin disk, the way everybody has thought for nearly 40 years. But matter is then delivered to this disk by stars plunging through it. And this would happen at a rather small radius, so that the extension, basically this accretion rate that is required to feed the quasar doesn't extend out to very large radius. The matter is delivered at relatively small radius by stars. Quasars then would be active during nuclear starburst episodes. So quasars would be strongly related to star formation, but to star formation that is very concentrated in the nucleus of a galaxy. It would depend on having an episode of star formation just around these 5 parsecs, around a 10 to the 8 solar masses. And of course, nuclear star formation would be very much correlated with star formation overall in a galaxy, right? Whenever you have gas going in the center and producing stars, making stars, normally you would have star formation going on across the galaxy because you'd have a lot of gas around. And so that would happen whenever there is a very high density of young stars present in the nucleus with rapid rates of orbital relaxation, maybe because, during episodes of star formation there's also massive clouds moving around, clusters of stars that haven't completely been tidally destroyed. So that would increase the rate of relaxation because you have a lot of massive structures around, and perhaps still residual violent relaxation from mergers that have started the process of star formation in the nucleus. So essentially that's the idea. During these episodes of nuclear starbursts, you'd have a very high density of these young stars, and this high density is what you would require to have enough material going into a central accretion disk, just delivering matter to this disk from stars and having the quasar shining. So stars would crash on the disk when their orbits become highly eccentric, just by the same process that, for example, the extreme mass ratio events are produced. You have stars undergoing random orbital variations. Then the way they go to the center is by going to high eccentricity and being captured near pericenter. So the key questions here are: how is the large black hole mass transported to the small nuclear disk? The black hole has to grow gradually by accreting all this mass, so you have to transport it to the small nuclear disk in the center. Why is the black hole mass related to spheroidal stellar system and not the galactic disk? and what established the M sigma relationship. And in our model, what we have, I don't know if I have a pointer here actually. Oh, you think. There is this is the whole range of radius I was talking about. 10 to the 9 AU is 5 kiloparsec, the size of the galaxy. 10 to the 6 AU is more or less the zone of influence of a black hole that here is taken to be about 10 to the 6 solar mass black hole. This is the 10 to the 3 AU is the region of the accretion disk where it becomes quite luminous. 1 AU, that's when you get to the Schwarzschild radius. So there is a region here, first factor of 1,000, where you have just a normal accretion through viscosity in the disk. And then there is the region where you have the galaxy here. And more or less at this radius is where you have similar mass in stars as in the black hole. But then over all these orders of magnitude, 3 orders of magnitude or so, the way matter would be transported in this model is that you really say that all the mass you have that has to go eventually to the black hole in the form of gas will turn into stars. As we said before, the disk should be unstable to making stars. So you go ahead and make all the stars. And then those stars will just undergo relaxation of their orbits to high eccentricity, and they will transport the mass here just by crashing on the disk at this smaller radius. And then material just goes into the black hole from here. In the model, we make several assumptions, which are not, we don't know if they're true or not. Some of them. So stars are slowed. The way they're captured is that they go through the disk and they're slowed down by ordinary hydrodynamic drag as they cross the disk and captured into the disk after many crossings. The surface density profile of the disk is something that will matter in this model, and we take the standard Shigura-Sunyaev model with a constant alpha parameter for viscosity. The captures will occur from very eccentric orbits. Relaxation will keep the phase space density constant, a full loss cone, at least at the large radius from which most of the stars are captured, which is about the zone of influence, because the black hole will have to acquire essentially all of its mass by capturing stars. So it has to capture similar mass in stars as its own mass. Inside in the inner region there, the loss cone may not be full, but that's not important, so much closer to the black hole. Then what we're going to assume is that we're going to see if we can find out if the rate of stars crashing into the disk and delivering mass is high enough by checking if we can essentially require you can maintain an Eddington accretion rate onto a black hole and then grow the black hole up to a mass that is related to the velocity dispersion of the stellar system around it, from which the disk has to be fed. So the assumption is that there is a steady state of mass delivered into the disk by stars. So the same rate at which mass gets deposited into the disk is the accretion rate at which mass goes from the disk to the black hole. So mass accreted from the disk to the black hole has to be equal to the rate of mass delivery from stars. Then the M sigma relation is established by the required density of stars for this mass supply rate. If we need enough mass deposited in the disk, we need a certain density of stars around the black hole, and that will tell us what the velocity dispersion of the stellar system has to be. Well, I'm not going to go through all the details about how one can, one does the derivation, but this is in any case published last year in Astrophysical Journal. But so the main idea is that stars are captured by the disk by this hydrodynamic drag. Typically, the surface density of the disk is much less than the surface density of a star. The velocities at which the star goes through the disk are very high. They're highly supersonic and also much greater than the escape velocity from the surface of the star, so gravity doesn't matter very much for a star. When the star goes through the disk, it slows down by a small fraction of its own velocity, but then because the orbit is very eccentric, the apocenter of the orbit can be reduced. Okay, so then essentially one can go through some arguments that I'm going to skip here, but one derives what has to, essentially from the surface density of the disk, how many stars there have to be so that over a certain time you will put a certain amount of mass in the disk. And we assume that well, so you can figure out the radius out to which most stars will be captured over a certain amount of time. This time is the lifetime of the quasar. So the quasar will live for a certain time during which the disk has to be continuously replenished. And this time, this age of the quasar, is the amount of time that the star has available to just undergo random variations of its orbit, and sometime during this period find the lost cone and be captured. You put all these conditions, the TS, the age of the quasar, is essentially the salpeter time, the time it takes for the black hole to double its mass at the Eddington luminosity with an efficiency about 10%, which is about 50 million years. This leads to a predicted M-sigma relationship, and to get this M-sigma relationship, you have to assume a surface density profile for the disk, which here we take to be go as mass of the black hole to the 4/5 over radius, which is this P, which we equate roughly to the pericenter of the orbit of the star to the power 3/5. And it depends on an accretion rate in Eddington units and a viscosity alpha parameter. This leads to a relationship that says that the radius of influence, the radius from which most of stars are captured, goes as the black hole mass to the 8/15, and when you put in the virial relationship, it gives you an M-sigma relationship. Mass goes as sigma to the 37th, or about 4.3 roughly. When you put in all the numbers, including the normalizations, you get the following relationship. Essentially, mass of the black hole is here, velocity dispersion of the stellar system is here to the power 37th, and then there is a dependence on, for example, the mass of the star, the type of star that is forming the cluster. Of course, the mass of the star and its radius affects the rate at which mass stars will be captured by the disk. The radius of the star is expressed in the form of escape velocity of the star over here from its surface. This normalization here of this M-sigma relation depends also on m dot. What do we assume for the accretion rate in the disk? We assume there is a steady state accretion rate. M dot here is in Eddington units. So m dot is basically luminosity over Eddington luminosity and divided by the radiative efficiency. And then it depends on this alpha parameter, the viscosity, because viscosity relates the accretion rate to the surface density you're going to have on the accretion disk in order to maintain that accretion rate. So you put in more or less reasonable parameters, reasonable numbers for these parameters, like, L over L Eddington 1 and relative efficiency of 0.1 and viscosity parameter 10 to minus 2, about a solar type star, and you get a normalization that's close to the observed one, or 10 to the 8 solar masses for velocity dispersion 200 kilometers per second. So that tells you that for these parameters, it is possible to have enough stars in this cluster to feed the disk at the rate that is required to maintain the Eddington luminosity, if you have this M-sigma relationship. But one has to realize about the various uncertainties we have in this normalization and this relationship we have derived when you try to compare these two observations, right? It depends on the values of these parameters, as I have already said, in the way expressed here. You also have to assume a full loss cone, and actually, so you have to assume basically that at the zone of influence where most of the stars will be captured from, the stars are undergoing relaxation fast enough so that over this salpeter time they will find the loss cone. And if you put in two-body relaxation and assume there was nothing else, this is not actually quite enough. So the relaxation rate will be too long and stars will not be captured. And this is especially true for massive nuclear black holes. If the mass is as high as 10 to the 8 solar masses, then of course the relaxation times get longer, right, with the mass of the black hole. And so you have to assume that there's some other process that increases the rate of orbital relaxation. Then also we have derived here this M-sigma relationship, but the velocity dispersion should be, in this model, the velocity dispersion of the stellar cluster within the zone of influence that's very small, 5 parsecs or so, at the time the quasar is active. And of course the observed M-sigma relationship is something different. We relate the mass of the remnant black hole that we observe when the quasar is dead with the velocity dispersion of the stellar system that is left a long time after the quasar has died. So the relationship between this velocity dispersion of the nuclear starburst when the quasar was active and the observed value today in the remnant galaxy, that's also an uncertainty. We have to assume that there is a constant relationship between the two values. It doesn't change much from galaxy to galaxy in order for that to be an explanation of the observed M-sigma relationship. One question that one can ask here is, okay, so we're capturing all these stars by the disk. The stars are going through the disk. They will go the first time, then they will reduce their apocenter, they will go many more times, then the orbit has to be gradually circularized and become coplanar with that of the disk until the star is embedded inside the disk, and it will just be inside then. But what happens to these captured stars? In order for that to become fuel available for the quasar, the star basically has to be destroyed. That matter inside the star has to go gradually accreting into the black hole. It has to become part of the accretion disk. And how will this happen? Well, basically, we think that the stars will be destroyed. They can be destroyed in several ways. For example, it's not clear if during the passages through the disk themselves, if the surface density is quite high, every time the star goes through the disk, some of the material may get peeled off just by the shocks that happen there. That's not clear whether it can really destroy the star in the number of passages it will go through. But then other processes, well, I mean, some stars might be destroyed actually by tidal disruption, as we were talking earlier with Clovis about this, that maybe they will just sometime get close to the black hole and be tidally destroyed. But another thing that happens here is that in this model, the rate at which stars are captured by the disk, it has to be very, very high. So that if they're not destroyed, then they will all be left inside the disk, and their numbers is so high that if they were there, then if stars did not dissolve, their density would be so great that they would collide with each other. You can count basically that if every star was in a circular orbit, then there would be more of them per unit of radius than they're able to fit in. So, you know, within the ring of size equal to the diameter of star, there would be more than one star in the disk. And so then they would have to somehow collide, and then they would coalesce. This would lead to stars that are more massive and more inflated, less density, more easily destroyed. And this process of coalescence would go on until the stars would basically become unbound and be destroyed. So sooner or later, most of the material in these stars will just dissolve into the disk and become available for accretion. Now, this has some, in this model, there might be some interesting consequences for LISA, and I haven't thought about this very much, so this is more basically a comment that I bring up for discussion. I'm not sure if I got it right or not, but just to generate some ideas. So in addition to main sequence stars that will be there during this starburst, there will be a lot of objects, of course. There will be red giants. These will have their envelopes destroyed, but they will have a white dwarf inside. So some of these white dwarfs will also be added to the disk. For example, if a red giant just goes into this lost cone, well, it will lose its envelope, but then maybe as it smashes into the disk, then the white dwarf will be left there. So there may be plenty of white dwarfs inside the disk, and this will not be destroyed so easily, of course, as main sequence stars. They may just be there inside the disk. There may also be collisions sometimes of a white dwarf with a main sequence stars, then the main sequence star will be destroyed. But then if you have collisions between two white dwarfs, presumably you have a supernova. Supernova will not be very much compared to what's going on in a quasar, so you may not have much of a consequence. But anyway, so you might have formation of neutron stars, stellar black holes, so you might end up with a number of those inside the disk, if this model is correct. Then this might produce perhaps some interesting extreme mass ratio in spirals. Of course, you might not see the hole in spiral, and it might be very much affected by the hydrodynamics of the disk. It may be that over some range of radius, some effect due to dissipation in the disk is more important than the dissipation due to gravitational waves, so you might not see the whole duration of the event. But nevertheless, you might see some fraction of it. If we just consider AGNs with black hole mass of 10 to the 6 solar masses, and an accretion rate that's close to the essentially Eddington accretion rate, 10 to the minus 2 solar masses per year for this black hole mass. So this would be an AGN with a luminosity close to Eddington luminosity. Well, let's say that 1% of this accreted material, if it all comes from stars, maybe 1% of it will end up as these compact objects. White dwarfs, neutron stars, stellar black holes that somehow get inside the disk and then they're not destroyed. So 1% of accretion in compact objects, then that means 10 to the minus 4 per year. If each one of them has 1 solar mass, roughly, would be going into the black hole. Well, if you have an event rate of 10 to the minus 4 per year from every AGN with this mass of a black hole, this might compete actually with extreme mass ratio events from inactive black holes. So it's something to think about. The model that I have discussed has a problem that, well, we're not quite sure how it may be resolved yet. It's the angular momentum problem. It's basically global angular momentum problem. So how do you keep this? Basically, the captured stars are selected from this very narrow loss cylinder in phase space. If the phase space is constant within this loss cylinder, then it seems that if you're just capturing these stars from this loss cylinder, then on average, these stars have zero angular momentum. But the more important problem is that counter-rotating stars are more easily captured, because when they go through the disk, of course, the relative velocity with the gas in the disk is higher than for stars that are prograde and rotate in the same sense as the disk. So then, if you tend to capture more stars that counter-rotate, on average, the mass that's added to the disk would have angular momentum, net angular momentum that's opposite to that of the disk. It would tend to essentially remove angular momentum from the disk continuously. If negative angular momentum is being added to the disk, then the disk could not be supported. Essentially what would happen is if you just try to add material with opposite angular momentum to that of the disk, it would accelerate the accretion for a while, but then that would not last for very long. If you just take material from the central part of the disk and with negative angular momentum, you would just make a hole in the center of the disk, so make the profile more extended with a kind of hole in the center, until the surface density in this region has gone down enough that fewer stars are captured. And then the only way that this would continue to accrete is if there is some other supply of gas further out, like normal flow of gas from a normal disk, so then the disk is not being fed by stars anymore. Something like this would happen. So it cannot be that you just keep supplying a disk with material that has a negative specific angular momentum. Two possible solutions. They have to rely solutions have to rely on the rotation of the stellar system. Obviously, the disk has to have some preferred direction of the angular momentum, and that can only come from the rotation of the stellar system around it. The stellar system doesn't have to rotate very fast in order to supply angular momentum to the disk, because the disk is very, very, very small, and as you know, in the Keplerian potential, the specific angular momentum goes as the inverse square root of the radius. So material coming out from large radius has a lot of angular momentum available. It's just that for the stars that are captured from this loss cone, it averages out to zero or negative, as I mentioned before. That's where the problem comes. One possible solution is that you have a quasar wind, and as the material flows in this disk to the black hole, when the luminosity gets close to the Eddington value, it blows out most of the material in the inner disk. It blows most of the inner disk matter, but it blows it out at less than the escape velocity, so that then this material will fall back into the disk at larger radius. So you have a wind model where you have a kind of recycling of the gas. It's blown out and then falls back at larger radius. Well, the effect this would have is that it would mix with matter coming from inside, coming from the stars with outer disk matter. Then what you have to have is that a small fraction of the accretion rate comes from a more extended disk. There would be a disk of gas anyway, because you know that in such a young, dense stellar cluster, you have a lot of red giants, for example. They'll be losing mass. They'll be losing their envelopes in this environment near the quasar. So somehow a lot of gas has to go near the black hole and form a disk. Maybe a small fraction of the accretion rate just comes from this disk. Then the stars just provide more material at low angular momentum, but the angular momentum comes from the material that is from mass loss from the stars. And then you have to find a way to mix this material like this wind. Perhaps another possibility is most angular momentum is exchanged in the final phase of orbital grinding, so when the star is already coming close to finishing circularizing its orbit and making it coplanar with the disk. The loss cone is then not very narrow, and maybe the phase space density, well, then it doesn't have to be full. The phase space density may be non-uniform, with more prograde than retrograde orbits. So in other words, the stars on retrograde orbits are removed faster from the loss cone because they go against the disk, so they're slowed down faster. But then maybe that would cause the prograde stars to have a greater phase space density in the loss cone, so then that compensates for it. If you have zero input of angular momentum in the disk, then there is essentially no problem, because the black hole is taking material from the inner edge of the disk with nearly zero specific angular momentum. So if we're adding material with essentially zero angular momentum, then we have a steady state. The problem is when the material comes in with negative angular momentum. Okay, in this model, essentially, if you were able to look at a quasar, take a close-up picture what a quasar might look like, Well, what you would have, the typical pericenter where these stars would be captured is hundreds of AU for the 10 to the 8 solar mass black hole, or basically hundreds of Schwarzschild radii. At any time, in order to supply the accretion rate that for this mass would be about 1 solar mass per year, thousands of stars would be found going through this region of several hundreds of AU where they are captured, going through their pericenters, crossing the disk all the time. So there'd have to be lots of them, plunging through the opaque accretion disk radiating at 10 to the 5 Kelvin. So if you took a picture, you wouldn't be able to see the stars. You'd see a shade for the star because it's cooler than the disk, of course. Probably you might also see star tails of matter, which might occur, when a star goes through the disk, there would be a tail of material lifted as the star plunges through, and then that would just go on some orbit and fall again later on the disk. So constantly you would have these tails of material flying around, put there by the stars. And maybe these tails could account for the broadline region, and there have already been other papers written about this. So basically there would be clouds around the quasar. It would be nice to find tests for this model, but it's very hard to think of any. If you could resolve the central parsec, then you'd be able to find out, are there all these stars there? But we don't have a picture of the central parsec of any quasar. We also think that there should be no evolution of this M-sigma relationship, basically, because that just depends on physics of the number of stars that surround the black hole, and this should be independent of redshift. You have all these stars evolving during the 50 million years or so that the quasar lives. Maybe, they have some effects on metal abundances. We don't know how much it would change, but in any case, the very high metallicities that are inferred in quasar disks, essentially they're consistent with this picture. We think there has been a lot of star formation in these regions. There should be, of course, a high density of stars in the nucleus, but this is when the AGN is active. This extremely high density of stars. But not today in the remnant black holes, we don't necessarily see a very high density of stars. Some of them, some ellipticals, have power law cusps, and some of these power laws are quite steep, going as r to the minus 1.5 or so for the density profile. But a lot of them have cores, and they don't have the high density of stars required for this model. But what can happen is that after the quasar phase, the density of stars can decrease due to various dynamical processes, such as black hole mergers, which may create cores in elliptical galaxies. We may also have a top-heavy IMF. There's increasing evidence that in regions of very high density, we have a top-heavy IMF, so many stars with a high mass. And then, of course, after a while, all these stars would have evolved, and we'd see very little light today close to the black holes in the center. We just have the stellar remnants left. This I'm going to skip because I haven't talked about. And when the disk mass is, a black hole mass is as low as 10 to the 5 solar masses, then it turns out that the disk mass that you would have in this model is similar to the mass of a star. Then this model would stop working. So we'd expect some break in the M-sigma relationship. Okay, so basically this is tests, and to summarize the talk. So a new quasar model is proposed in which matter is delivered to the accretion disk by plunging stars, and these are perturbed by relaxation processes to highly eccentric orbits, and from there they're captured. The model accounts for how enough matter is brought to a galaxy nucleus to fuel a quasar, first of all. So it basically solves the problem of how you go over these many orders of magnitude to bring the matter close to the black hole, and how you make the black hole so massive. And then it also explains the origin of this black hole and the bulge M-sigma relationship, providing an alternative explanation to all these feedback models. So basically that's all for this talk, so thanks. So you mean accretion onto the white dwarf, but this would be accretion of gas, or? Yes, accretion of gas from the disk. Yeah, I'm not sure how fast it would accrete actually. it's not going to be in the disk very long because, I mean, see, we think that the quasar may live for a salpeter time, 50 million years, but the disk has a much smaller mass than the black hole, say 1,000 times less. So the material in the disk only has 50,000 years before it is accreted. And over this time scale, probably, you know, you'd have too much luminosity to accrete very much into the white dwarf.
I'm a bit concerned about the spatial scale of the region that is actually coupled with masses of black hole. For example, in your generic elliptic, where you try to explain the connection between the inner 5 kiloparsec and the mass of the black hole, but that would be a very complex elliptic. I mean, for example, for a lower mass black hole, let's take our own black hole in the galaxy,
Yeah.
the radius of influence is only a few parsecs, the
Yeah.
body is a few kiloparsecs. So, in a sense, needless to say that in fact it's surprising that in the context of this knowledge, that the M-sigma relation actually pertains to the much larger scale.
Well, but this is true. I think this is true for all black hole masses, also for the 10 to the 8 solar mass. And as I mentioned, essentially it is this problem that we find an M-sigma relationship to the velocity with the velocity dispersion of the nuclear starburst at the time the quasar is active. Then,
Probably because you're assuming the thermal that the velocity dispersion is constant all across the bulk.
well, so then basically you have to assume this, or otherwise there might be a constant relating to them. That is not necessarily 1, it might be close to 1. But it would affect, this constant would affect only the normalization, and the normalization depends already on various other parameters, as I mentioned here. So, I mean, yes, of course, this is a big uncertainty, how it relates to the velocity dispersion at larger radius, yeah.
You have actually two types of correlations. One is between the massive black hole and the central region, which are affected
Yes.
by the process, and then another correlation to explain the coupling between the central bulk of the
Yes, yes. So in fact, yeah. So the way this could arise is that when a galaxy forms, you know, the density profiles might be quite universal in a spheroidal component, so that you always have the same relationship between this velocity dispersion at the radius of influence and the velocity dispersion at the half-light radius. But then, what happens later in the evolution after the quasar dies may vary from galaxy to galaxy and may explain the different slopes that you find in the central parts of ellipticals.
I'm going to break that off here. Our organizers are concerned that we all have a chance to eat lunch. So I think let's eat one more time.